Well, I think it's time to go on. I hope you enjoy your coffee and also the next presentation from Turku. Right? Not Turku. Yeah. Turkey. Yeah. So, please, Jukka, we can start and then we have plenty of time before wine and coffee. Please. Yeah. Thank you.
This time I'm presenting something that is still going on. So this is open to suggestions if you have there any. And if you have noticed in the morning that we have a lot of components that new technologies emerging, and this way we have tried to find the stepping stones for different groups using the sea area, not just the Fairway. So this is a little bit different, let's say, approach. You could say that it's demand-driven, but it's not actually true, but I will explain why not. The other thing is that I'm not concentrating on remote piloting on that, because we think that this is pretty, well done. It's already working. And I come from the Marikka team. We happen to have the same last name for a good reason. And then Gabriel is from Germany. Jonas is from our team. And what we promised in the beginning of this project was that safety and efficient. We promised to do it by 2025. And this is the outset of finding the stepping stones that how to proceed. This is the whole Fairway structure. And you notice that the definition of the Finnish definition is divided in two. Fairway is officially an area intended for the use of waterborne traffic, delimited by channel's edge lines. So we are stepping out of the channel, and we are also staying out of the shoreline. So we are, let's say, from the shoreline to the territorial water border. That's what the area what we are talking. And how are the fairways maintained in Finland? So how are they classified? So we have two categories basically. The other one is all the time open. And this is open when there's no ice. And they are maintained in a certain way, which means that we are taking care of the fairway infrastructure, like you were mentioning, that is dredging, so that the depth can be guaranteed and that all the visuals are in the right places. Here you see how the ships move, big ships. And I know for sure that there are also boats on this area, but it doesn't show because they are outside the fairway. And now when we are talking about rethinking the fairways, we have been concentrating on accidents. The Finnish accidents, 6. The rest of accidents are here. So our system are safe. The waterways are safe. There's no denying of that. And also the collision and collision prevention and rescue systems, they also work fine. And this is our responsibility, the area. But what we are talking about here this time is that, okay, you see, here are the areas, how they are divided in different types of sectors and who is responsible of doing what on these areas. And if we look at the accidents and incidents, this is the accidents. Not too many types of accidents, it's only in Finnish, but let's say that they are hitting the ground. And if we look at the incidents where we try to improve the situation by, with actions by vessel traffic system, which tries to actually protect the people of having these accidents, it seems that this piloting is already taken care of. I think it takes the second spot here. But if you look more carefully, most of the accidents what we have or incidents are about to happen either in a technical sense that somebody ends up in being in a situation that cannot navigate anymore, or navigating off fairway. Yet we know that on this blind spot there, people can move safely, but we don't consider that fairway. Should we? That's the question. Should we? And how can we improve the situation so that we can provide similar safe services to the rest of the seafarers that are not the merchant ships on the fairways, to the people who are moving on the not so safe areas. Can we do it? And we think firmly that with the new technology we can, and we can start already now. Let's move ahead. So, better situational awareness of the other seafarers' plans. This is a traffic system. It's not just a ship going through the fairway. We have to understand what the others are doing. Like it was shown on the Novia case, that there are these ships that we don't know whether they are ships or they are birds, whether they are stationary or they are diving. Okay. The other thing is that we divided this into two categories. Distress means that there's something about to happen, but emergency means that it has already happened. And there are something that is also worth noticing. Here, we should be able to predict hazards. And I say that we are not utilizing the information we already have. We should. And we should anticipate the evasive maneuvers, because this will become very vital if there are any autonomous ships on the fairway. Why? We were dealing with the Navy, and the Navy guys said that there is a kind of alliance that thinking that how the autonomous ships should behave. And they have defined the rules, that how are they behaving. And if we go and check the rules, it's a kind of a call rec for autonomous ships. SARUMS is the name of the consortium. They define by the categories of ships what kind of maneuvers they can take. And if you take any of these ships and move it to the Finnish waterways, they cannot maneuver. Or if they maneuver, they cannot do any evasive actions if there's a hazard situation. So this leads to the long-term view that probably we should think in that way, that what about the other seafarers? Should they bear responsibility of their own actions? So it's not the responsibility of the ship going the fairway. They are overburdened by this information already that we are providing. But these guys who are there outside the fairway should have better information, because they have better capabilities of maneuvering and evading risks. And then when we end up in an emergency situation, we looked also into aviation and land-based traffic. Especially in aviation, they have 3 golden rules. That when you are in trouble, you shouldn't gain more information, but you should do only 3 things. Navigate, know where you are, and communicate, because you are needing help. So the fairway should provide help to this kind of actions, not provide and overwhelm them with information, but stick to the original and most crucial information that you need in the emergency. And of course this needs automation. That was the safe part. Then the efficiency part, routing and sustainability. You can avoid storms, you can use open water area, you shouldn't go to the certain restricted areas, and this can be done on the fly, especially for the big ships, but also for the other ships if we provide the necessary information. And finally, which is still pending, is this business model. The business model has something to do that. Here you see 21, 19, and what kind of growth rates we have there on the white area, crossing also the fairways, that what kind of services they might need. How many more ships do we have there? 669 versus 687. Okay, you ordered more, but still that's the case. This is not a big market, because you install the equipment on a ship, whereas here, when you are talking about these 200,000 motorboats or rowing boats, canoes, skiers, so on, you have there million. And if you can sell them something, you can sell it also elsewhere than in Finland. You can also sell this somewhere in Finland, but there's a competition out there already. But this market is hugely underestimated at the moment. Okay, why should we focus a bit more on the recreational use? It's a traffic system, and they are there in among these ships that go the fairways. And that means that, okay, these guys come from off fairways, and they are crossing fairways, they don't look out necessarily, and there has been constant complaints about their seamanship that is deteriorating. And especially because of the invention of other watercraft, it means that the differences between the different seafarers is growing. So should we actually serve this customer group as well? Not just the fairways. You know, the old good seamanship is that when it gets foggy, you go in the middle of the fairway because it's safest, the deepest part. Okay, so what I'm saying, it's an attractive market opportunity basically, but how could we then start building on this? First of all, what does it take? Information of vessels. Situational awareness can be probably improved by a couple of things. We already have a standard on navigational warnings. That includes the weather information. You can mesh and put it available. And this can be delivered over the internet. The other thing is that how do we know the movements and plans of big vessels? We have a compulsory GOFREP reporting system that is at least in the Gulf of Finland, but at the moment I think it's not available for the Gulf of Bothnia, or is it? No, but we can also do that, I will show you. Because then we get the route, destination, and the estimated time of arrival, so we can have approximate location of the other vessels in the proximity of the big ship. Yeah. How do we share the information at the moment? You must have VHF radio. I don't. You should be able to communicate over VHF. I don't have the device. I don't have the license. So in the long run, we have a promise that this VDES will improve the situation by integrating it with the base stations. So we have basically there also this kind of let's say multimedia information available, or at least some sort of a data transfer. And the R mode improves AIS because it's giving the backup for the GPS signals, so we know that where the ships are moving. So what we know for sure where the big ships are, but we don't know where the small ships are. Or do we? AIS on the internet. Small ships won't have AIS at the moment because it's imprecise and it has to be improved before it can be taken into wide use. There are of course differing opinions on this. But one thing is that we could actually broadcast messages to all users over 4G or LTE network. Let's dig deeper into this. Here's the GOFREP idea, so that you have to announce where you are going, so you know approximately when the ship is arriving at this route. And of course VTS follows all the time the movements of the ships. And we have a similar place at the Åland Sea, where there's this kind of a liikennejakoalue, I don't know what it's in English. But anyway, we could require from that area as well the GOFREP kind of announcement. Then we would know how they are moving at the Osterford. And then, pretty new stuff. We were tracking actually Osiris work, and we found these Chinese guys and then some Canadians and Australians working on this. So you have pretty good predictive algorithms already following the correct rules, so that how you should evade the other traffic, or should you stop, or should you give way. And when these algorithms are available, they are developed, they are already tested, we can downscale them to 4G false, so that the rest of the traffic might be able to follow that, okay, we know roughly, based on this GovRep, that there's a big ship coming, it's here around that time, and we know that we seem to be in that area around the same time on its way. And now when we have this information, we come to the tricky part of communication. Like it was in the elements of the system, these, the whole thing that Marika was presenting with Heidi there, that we have these kind of information available, but how can we transfer it to other parties? First of all, we have to standardize the messages. So here you see an example of very, very traditional way of expressing that you are in distress or you are in the emergency. This is what you have to send into the ether. But this could be also many of these things automated. You know, vessel ID for sure. Position comes from GPS or in bigger ships from the VDSR mode. What is going on, you have to tell. What kind of assistance you might need, might not be essential information. Number of crew, you know, and additional information if you need. This could be automated. I'm leaving now for a ride with Marika on a watercraft, and we are going to there for a trip. I just checked that this is my vehicle, and now we go. And now we will get the information that on the way we will pass Viking Line and some fishing ships. You see what I'm talking about? We know. Why we know? Because the GPS is on the phone. Right. And then our application says that slow down. There's this straight, it's too narrow for you both being there at the same time. And if you go closer, you start communicating with the VTS. It can be automated, so VTS knows that this stupid pair on this watercraft is now pushing the same straight simultaneously. They are so stubborn. So we will be in contact with them. And now comes the tricky part, that how? Because we don't have VHF. How? This works fine for bigger ships. We suggest that building on existing technology already now, when we are updating Fairway 2 for the archipelago, we should try expand the 4G services to the seafarers. So VTS could send us an alert that you are going to the wrong place, wrong time, and if we don't obey, they will call us because they know we are there. How do they know? You know, this system has a kind of a register of users, registered users, point-to-point connection. They know all the time where we are. You can try it with your own phone. So there's a phone location register which tells about me, about our watercraft. And when we move around here, it will move us to a visiting location register. And they know our spot. They know the approximate spot, but if we design the system right, we will set the GPS signals every now and then. Our precise position might be of not that important. One base station can serve 1,000 users, so that means one stick, they're standing on the cliff, and we can optimize it. So should it be enough for these other people? If not enough, have you heard of rock concerts but still serving the phone connections? They can update it dynamically. And then what we need, we don't even need fiber there, by the way, because it is now connected with radio links. The base stations are linked with each other by radio links. And we have been considering this carefully, therefore, that 5G fits other purposes, but not this kind of remote locations, the white spots, but it fits very well these crossings and harbors and so on. And 3G is now getting out of the service. And this is how it looks. This is the coverage of 4G LTE network in the archipelago, our territorial waters. Not bad. Okay. It would take some private public partnership. Here you see how is it possible that this looks like this, but it covers the whole FC area. Because if you go to cell mapper, those of you who know will check that this is what is the area that is serving. Because you see users have been moving around there. But you have these beams on the same stick. You see that it reaches farther out. And you have other operators that show you that this is this area that we are covering. So roaming is the key. And the authorities must cooperate with the operators, probably manufacturers, that we got these services done. And as I told you, we are still in the progress of doing this thing. And even though the project is running to an end, we cannot stop. This is so important that we have got a clue what to do here. And of course, you don't have to agree with us because this is our view. So you can say that this is nonsense, but please tell us that where to change. We'll do that for the design. We have now the service elements, but we don't know in which order we should introduce. But if we take this kind of all seafarers approach, we can take a couple of people, probably a user group like the hovercraft people or canoers, and provide this information with using this GOFRED device information, delivering them over the 4G LTE, and then use it for this kind of emergency situation to improve their safety at seas. So would you be willing to be on the trial? Because now you have nothing. Of course, those richest people have, because they can invest in VHF and take the licenses and so on. The other thing is that there are other issues that are getting more of importance, and one of the things is that we have to avoid vulnerable areas. HELCOM has been doing a long-term, very important work of showing that you shouldn't move on this area due to erosion or that it's a spawning area for some fish or birds and so on. And the other one is that we have to somehow reclassify the whole fairway structure. And how can we do that is actually that if we implement this technology, it means that we can follow the users like on the map, that where do they go? It's safe to move there because they have not hit ground. At the moment we also have some fairways that are not maintained by the government, but it's maintained by municipalities or some associations or something like that. Why don't we take advantage of that? Of course, I know the army guys will tell me us something of that. And finally, when we have these bits in place, we can create a roadmap that for this user group, we must invest publicly. For this user group, we will provide them with the information of the other ships and the locations and hazard zones, and they can build their own applications. Because you can see that for canoers or ice skaters or hovercrafts, the requirements are different. And we know that you can only do it. There are two companies here. Mobilizing seafaring groups to gather information and where we can move safely, and improving the algorithms that we have already seen here, and how we can share the data. The authorities should be responsible for the data quality, that it's available and it's correct and it is timestamped and you can use it. And finally, this needs more education. The whole traffic system will change eventually. That's how we see it. That we have to start rethinking the fairways so that it's utilizing this digital part, and don't think that we cannot communicate overseas. Thank you.
And then a question. Then.
Vesa-Marttinen Jepson, thank you very much. This is music to the ears of a trucking businessman. And the comment I have here firstly is that due to the GDPR, the people tracking on the shore side never really took off in Europe and in US. So I'm afraid that if we go to this one, kind of personalized data to be followed by authority, you might have an issue.
No, you have to have a user consent.
But yeah, never mind that. What I say here is that the way it can be solved so that you can identify the location, the way it can be solved where it is going, the way it can be solved that you can push a button of an alarm, so that gives the location, is that you would have IoT device on board the boat. It will cost you about 100 euros per boating season, and you get 5% discount to your insurance. So you're actually covering what you pay with the savings. And I think this is very doable business case for all those boaters out there. And as such, we could implement this for next summer to thousands of boats.
Thank you. That's an example that we cannot invent these kind of things, but together we can do.
Exactly.
Yes.
Did I understand you correctly that you mean that all pleasure boats, even small boats, should
No.
be with this?
They-
Where's the limit?
Where's the limit? The limit is that how well we can attract them to this system. Because you know there's no perfect solution. And of course, if you could compel them with the legislation, so they will still miss it. They won't have it all.
Anyway, it will
But
be a
somehow-
interface.
Yes, yes.
So it's mostly for professional use.
No,
No?
I could take it. I'm not a professional.
Yeah, but it should. You mean it should be like
Renting boats, these kind of things, they could have
only
it.
for those who want it?
Yes.
Oh.
Because it's anyway better. There are a couple of corollaries here that I'm very much, hesitant on talking about that we want to push a standard. No, that's not the idea. You have to put the standard on a fairway when you are remote piloted, and so you know the responsibilities, that's the such things. But now we are talking about the other users, and they could take it by themselves. And one thing is that we'll do some cross-checking with this liikenteen automaation suunnitelma, is that this is already ready. Here's the blueprint for the whole stuff. It's done by IMO. This is the R-mode VDIS infrastructure where it is explained, and this interface is already defined into our standards. Just go and do. Thank you.
Okay, thank you. Next presentation is from Tampere.
Okay, good afternoon, everybody. I'm Bill Silverajan from Tampere University. And my talk is entitled The Fairway of the Future, Important Technical Learnings. And although you see one name here, a lot of these learnings have arisen because we work with a lot of partners who have provided us a lot of useful information across different work packages. And one of the things that you have to understand is that I am unapologetically a technologist, and which basically means that when we entered the project, we had a huge gap where we had to study a lot of vocabulary about the maritime industry, how things operated, and building up our expertise to work with the partners. So having said that, I would like to also say that this is still also like what you guys said, we are also in work in progress, we are still continuing our research. So what's the maritime industry like? It is really one of the oldest industries known to mankind, and it's heavily regulated by maritime rules. And it remains a very vital part of the global economy. So 9% of trade around the world is done over the maritime routes. However, we see a lot of investments in digital transformation with the introduction of smart ships, smart ports, and obviously this has to impact the technology that's being used in fairways. And I'm going to use the word waterways here because that was something that was never actually discussed. But when I was studying literature, I discovered people were talking about fairways and waterways, and I kind of assume waterways mean things that are more inland. But coming from an inland university, that's something my colleagues on the coast might know more. Okay, but anyway, digital transformation has significantly advanced, and it's based on advances in terrestrial connectivity, industrial IoT, things like data management, image processing, mapping technologies, AI and ML. And all of these, I'd like to just show you a couple of slides and to understand how they're going to impact the Fairway development. So this is actually a pretty old slide. It was taken from a project called Munich, which kind of shows the way the Munich project envisioned how autonomous ships will eventually come to be a reality. So today we're actually in a situation where there are lots of manned ships, right? So there's a lot of ships with radar, ACDIS, visual displays, and so on, and there are people on board, and it's a very traditional way of doing things. Eventually, we are considering remote ships, and that is kind of interesting. When you talk about remote ships, there are actually two kinds. One of the remote ships is when you actually have these remote ships, which are people can be reduced on board the vessels. They don't necessarily need to control it. They might be looking towards operational things or handling cargo and things like that. And the other one is where you actually have a remote operator who's actually going to be remotely controlling that ship. So there's automation involved. But essentially what you're looking at is a reduction of humans on board the ship and maybe an increasing intelligence. And at some point in the future, which is of course still up for debate, we're going to see autonomous ships coming into action. Perhaps we already have some these days, but we don't necessarily have the ocean-going vessels which are autonomous ships. We might actually have autonomous ships ferrying between the archipelago, transporting cars and things like that. That's already kind of very possible. But ocean-going ships, we'll see how it goes. And then again, around the world, in terms of smart ports, there's a lot of activity as well. So Singapore was very heavily mentioned as an area where there's a lot of activity around the maritime, obviously. So the Tuas Megaport is already, there, I saw some press release that they've already started operating in some limited fashion, but it's supposed to be a fully autonomous port. At the same time, there you have places like Rotterdam, which don't necessarily need to go fully autonomous, but they're teaming up with technology providers to digitize the operations so that they can provide some digital twins. So from here, when we started with work in this project, we started to think about remote piloting and the Fairway. And sometimes we need to separate what the remote piloting system is and what the Fairway really is. So two developments took place concurrently. Firstly, we had to think about the intelligent Fairway as an infrastructure or platform, and what actually this intelligent Fairway or the waterway can actually be. And I just started to list out things here that could actually be part of the intelligent Fairway, which could facilitate remote piloting. So we look at things like sensors, for example, bathymetric sensors, acoustic sensors, positioning systems, movement detection system, and environmental sensors. And all of these have been covered today in our discussions. Some of these are producing data that is at rest, so you actually have mapping and topological sensors. Some of them provide dynamic data. And obviously, one thing I should have included here, but which I didn't, were the camera systems, which is extremely important in the Fairway areas as well. So they do both videos as well as photographs, and you can do image analysis on that. But then with all these systems, you need to do processing. And when you do processing here, you think about visual analytics. There's so much data that will be generated that we need to think about sensor fusion, so you don't necessarily have to send everything to the cloud, and effectively congest the radio traffic, trajectory detection, and forecasting. So different kinds of algorithms can be used, different kinds of machine learning and AI methods can be used, but all of them require processing power. Then there's also communication and the cloud. I just wanted to put them into one area, in a sense that a lot of these involve infrastructure that you need to build on the Fairway itself. Some of them are base stations, some of them are transponders, some of them could be gateways and access points and equipment to facilitate VHF. But on the other hand, the communication doesn't necessarily need to go to the cloud. So there could be base stations or gateways that exist in different parts of the Fairway that actually produce a kind of a mesh network or multi-hop technology. So not everything needs to be connected so that it's going over center. But then again, you have auxiliary systems. These are systems that could be considered to be part of the Fairway, but they don't necessarily need to exist right there within the Fairway's platform itself. So there could be services that are brought in so to make the Fairway intelligent. All right, so and things like BTS, NIS, and things like that go into this area. So with this idea, we could consider then what kind of services could actually exist in the Fairway. I'm not very good at drawing, so please excuse my drawing skills. But I hope this gives you an idea that the cases that we are looking at, things like navigation. Navigation could be not necessarily, we're not only looking at remote piloting, we're looking at navigation in general. So even with ships coming into the waterways and fairways, they would have enough information to do safe navigation. The safety, there's distress, then there are operations around the fairway, things like ice breaking or harbor operations that need that, and also leisure services. Now, there's a reason why I didn't put remote piloting as a service here, so please excuse me for doing that. That's because I could not really find a category where remote piloting actually fit, because remote piloting fits in multiple areas here. It is improving navigation, it is improving operations, but at the same time, it is improving safety. Not only because you have less pilots going into the water, but also you're improving the congestion in the water itself by having less pilots out there, less boats out there. The waterway is less congested, and that naturally improves safety. And another, I would say, side target of having remote piloting is that it reduces carbon emissions. When you actually have remote pilots, there's less carbon emission. So in a way, remote piloting fulfills multiple needs. And my next few slides are going to be about what we did and what we found. We were involved in the technology work package, and we needed to support multiple business partners and technology providers as well. So if you had listened to some of our previous talks in the afternoon, we were involved in building test beds. And why did we do that? Because we needed to firstly understand what the Fairway really was and what the remote piloting needs are. So we used it as a means to understand this infrastructure, what this infrastructure needs to be. So it's a very fundamental building block for us. And then essentially it's one of the nicest things about having a test bed is that it formed a kind of stepping stone to understand what you need in order to provide a digital twin. And at the same time, one of the requirements that we actually had was how to emulate things like traffic shaping, how to develop and deploy shore-based maritime services, and as clouds and data servers. So we need to understand a lot of these things. And when we started doing these, we really began to understand the needs of the networks, the needs of what traffic characteristics we need, so and what kinds of addressing reachability needs that we actually had. And then we came to the conclusion, what exactly is the edge? When we talked about edge computing, we want to think about what do we need to do to understand what the edge really means. Is it the fairway? Is it the vessels that are coming in, and so forth? To give you an example, there is work going on with object detection and image decomposition. And when you look at this work, for example, real-time video surveillance, the algorithms that actually are running, they don't necessarily need to run the edge, they can run the cloud. But then again, there's another possibility that they can actually run the device. You can distribute interest with the device, do some of the processing there, bring it to the gateways, do more processing there, and then you bring it to the cloud. So we need to think about how to do this kind of work in a feasible manner. So provisioning the edge infrastructure for testing, digital communications, traffic shaping, and the integration of various network topologies was very important. And finally, we were thinking about how do we deliver connectivity to the sensors and equipment. We have to work with standards organizations to understand those things. And finally, as you might have seen some of our colleagues talking about today, to understand, model, and also visualize cybersecurity threats, cybersecurity risks and threats. And lately, we have also been working with the university to understand how safety and security can be incorporated here. So, connectivity considerations, there's a lot of talk today about LTE, and when the fairways are very close to shore, LTE coverage, especially in Finland, is excellent compared to some of the places I've visited, which was incredibly unspeakable. But anyway, in Finland, LTE is excellent, and it has provided a very good basis for doing our real pilot experiments. But nevertheless, different radio technologies are still needed to meet connectivity needs. I'm giving two examples here. Firstly, fairway sensors and equipment further away from the coast or in blind spots need connectivity as well. And when you looked at the different kinds of sensors that we were talking about today, not all of them supported cellular connectivity. You need to think about some other bridging technology. And they may not just be Wi-Fi or cellular, they might be something else as well. So you need to think about radio technology in general. Obviously with 5G coming up, that's going to be a good thing. 5G also supports beaconing. That will help a lot with piloting needs. But the other thing also could be that, especially vehicles or vessels coming from outside Finland, outside the Nordic areas, they may not necessarily have the ability to roam into Finnish waters and use LTE immediately. So many of these vessels, they might be equipped with multi-radio technologies, VHF, satellite, and so on for ship-to-shore communication. Then we talk about communication considerations, and here I have a couple of slides to talk about communication considerations. Firstly, I want to talk about the AI system. And apparently, from my literature study, the first attempt towards digitalization of maritime transportation was actually AIS. And its main driver was safety, and the main goal was broadcast communications. But then, with the development of new services and the support for application-specific messages in AIS, things got very, very advanced. So to prevent overloading the system, ITU is standardizing what we call VHF gas system, which is basically a hybrid of terrestrial and satellite communication. So that's one system, and that's in addition to using terrestrial or satellite communication. And satellite communication, there are two different kinds. You have the low Earth satellites, and then you have the geosatellites. So in our program, we had a general consensus that IP-based communication would emerge as a dominant technology, and I'm talking about IP-based communication for voice and for sensor data and so on that is not based on safety or security needs or distress signals. But what communication protocols that we use on top of IP, that becomes extremely confusing, specifically when you talk about sensor traffic. The solutions are use case and business specific currently. So depending on who your solution provider is, it could be based on some open standard, or it could be based on some industry practice. If you're sending data to cloud, for example, with Amazon services, then what you do is you take what Amazon tells you to do. And then when we talk about communication paradigms, they also differ based on the needs, whether it's publish subscribe or REST or RPC. And then we looked at the different protocols that could be used, and at the transport layer, you have things like transport layer security or datagram transport layer security. And then you have things like MQTT for publish subscribe, or then you use REST-based systems like HTTP and COAP. But then, for sensor data, these could be transmitted over a very wide variety of wired and wireless networks. And they can conform to, when they talk about standards, there are different standards. So there are MMEA standards, there are CAN bus and so on, but then over IP networks. When we talked about payloads, JSON is becoming very, very dominant. It's very well supported using HTTP APIs. So from the perspective of using third-party provisioning systems, that's a good solution. And one thing we also discovered is that it's a very easy format to work with. You can convert it, you can adapt it for different purposes. So for example, XML is very common for instant exchange. Then when you want to do things like sending JSON format to the edge, and you need to have some very good compression, then you can compress it further. But there still seems to be a very big lack of these data models for doing these things. Okay, so security considerations depends on how you look at it, but compared to other industrial sectors, cybersecurity awareness is rather low in the maritime area. It's supposed to be so low that they actually expect more attacks. I'm just giving some examples that we found. So this basically shows certain things that could be a problem. Effectively, we're not only talking about technical problems. We're also talking about a general lack of awareness. So you can basically take over AIS information using a small Python script. You can do GPS spoofing, like was already mentioned. Ransomware attacks are common, and then using default names and passwords and so on are pretty much a problem. So what we found was that, particularly when bandwidth is abundant, then the choice of security mechanisms and protocols and so on are not really that different. But then when the radio signaling costs are very high, then you find that application layer performance really does not matter. But when the radio channel is congested, lossy, experiencing severe latency, then actually using transport layer security becomes almost impossible because they break. The technical reasoning behind it, if you inspect packets going through, are that they cannot establish any sessions. So in these kind of scenarios, what you need to do is to consider, instead of using transport layer security, you send application layer protocols, but then you have to encrypt and do decryption on the application layer itself, and then use something like UDP to transport your data. All right, I'll just skip over a little bit. So with data models, you need to figure out how to do these things with scalable data models. They need to be extensible and flexible, and also the data models should be able to be of a format that allows expressing multiple measurements occurring within a specific amount of time. So data modeling is something that essentially people talk about JSON or how the payload is transferred, but data modeling is something that usually doesn't become part of the conversation. My last slide says that looking forward, I was looking at the C4 value program as a technical blueprint for two things. Firstly, for future Fairway infrastructure. And it has been really informative to understand what the future Fairway could actually comprise of technically from the perspective of remote piloting. Then again, when you talk about future Fairway navigation as a technical blueprint for enabling remote piloting, that is even more interesting because we had a lot of trouble getting the demos going on. And as Marco mentioned, also mentioned that we actually started with one harbor, we moved to a different harbor, then we moved to a different harbor, and finally we got one night to do everything, and it was done. It was done, it was successful, there's a press release, which kind of shows that it's already technically possible to do it with a very minimal set of technological requirements. But then again, when we try to think about the conditions where you need remote piloting, where you might have extremely choppy waters, or when you have a lot of congestion on the systems, that's something that we need to still discuss. How do you actually increase safety and security of piloting services? Thank you.
Any questions?
Not a question, but more an addition or a comment. Thank you, Bill, for the presentation and for the slide about cybersecurity and using this TLS or DTLS. For creating the session using like satellite connection, then it's like impossible to create the session using TLS or DTLS because the key exchange is not happening. And then this is why we try to use other protocols. It was one of our tests together. And we thought about the object security and using OSCORP, sorry, and then ad hoc for the key exchange. It's a lightweight protocol for key exchange. And actually with that one, it was like happening for the key exchange. Even if we are using satellite connection, we are expecting a huge latency. So this is giving an idea that like for some specific use cases for the maritime, also thinking about changing the application layer protocols could be like a solution. Maybe for this scenario, I can use co-op over DTLS or HTTP for TLS. And then for some use cases, for some scenario, I can think to use other protocols that could work with satellite connection, for instance. So also like the scenario, the use case could control the use of which protocol for the communication. But like just an addition for the cybersecurity side
Yes.
and the protocols used.
Yeah, what about Quick? Is it similar to DTLS? Maybe?
Quick was a very interesting protocol that we tested, and it was somewhere between using Core over DTLS and using Core with ad hoc and also Core. Essentially, what was its weak point was that it does a similar session setup as TLS does. And what I couldn't understand, at least I didn't have time to analyze because there were lots of packets flying through, was whether it recovered from that to actually set up with its timers. That, for example, if you cannot set up a session, then it tries more aggressively to set up something. So Quick was kind of behaving, but you saw it happening after a very weird amount of time, and then suddenly packets started going through. So it did work. It was resilient, but it wasn't as resilient as I thought it would be.
Okay, thank you. I think we're gonna follow out. Next is Patrick from Ericsson. 5G for fun original, please. Thanks.
Try to contribute.
Yes.
Could you understand?
Hi everyone, Sanna from Ericsson and 5G in maritime. So very, very short introduction. I think most of you know 5G is the next generation of mobile networks, and it brings improvements across the board from performance to security and so on. And in maritime, 5G can provide high bandwidth, low latency, secure access and like secure communication and access to various services. There is things like ship to shore, between ships, port authorities, remote locations that we have been talking about today, and various other services that will need some form of access. And especially when we are in the Fairway, the wireless approach is naturally the one way to go. And also currently ongoing standardization is looking at how to bring satellites into the picture in 5G, so that then also brings 5G possibilities to open sea where current base stations don't really have the reach. Yes, and yes, so in this presentation we'll actually more look into how 5G can be used to provide isolation, access control and robustness for business and safety critical operations. So if you think shortly about maritime networking, so I said it's on the ship, between the ships, ship port, in port, and between various actors and authorities in maritime context. And these services, I imagine, I'm not in maritime business, so I might be wrong, but I assume that a lot of the services are only meant for a certain subset. So for example, port authorities would have access to all the services, a visiting vessel might have access to a limited set of services, and tourists on a cruise ship might have no access to any these kind of maritime services that are meant for navigation and various purposes. There can of course be also publicly available navigation related information and services, for example for leisure boats, but if we think on more the enterprise side, this kind of access control, I would say, is important in maritime context. And the other thing that is very important is availability. So I think people might have noticed that, for example, New Year's Eve at 12 o'clock, it might be a bit challenging to make a phone call because the radio access is still limited. It's a limited resource. You cannot kind of put unlimited amount of users and data on there. So this is of course an issue if you're relying on wireless access in maritime scenarios. You always want to have guaranteed performance. This means also that availability is a must. And might seem like a bit of a challenge, especially if you're using public access. 5G provides a bunch of isolation mechanisms, and they, together with traditional networking and security solution, can kind of be used to build a secure whole. And how I envision things is that for example, a port or maybe it's a national maritime organization has a kind of private enterprise network where you run these services. And then 5G could be used for providing them the secure access and reliable access to this enterprise network. So first, a quick look at the 5G network. So on the left-hand side, we have the UE, which is basically the end device, for example, your mobile phone. It connects via the radio access network, the RAN, to the 5G core network. And in the core network, there are so-called network functions. Here are some of them, but there are a bunch of them, and they are not really very relevant in this presentation. The important one is here the UPF, user plane function. It acts like a gateway between the core network and some external data network. You can connect to some public network like the internet, or you can connect also to private networks. So for example, an enterprise network. And in this talk, then I'm thinking more like, for example, this, let's say, port enterprise or private network, where the port services and related Fairway services are provided. And from one user plane function, you can have connections to multiple different external networks, and one device can also at the same time have multiple connections. So it could have one connection via UPF1 and one connection via UPF2. Okay, so yeah, I will stay here for a while. I will next present then 5 different enablers or solutions that 5G provides that can be helpful when wanting to kind of deploy a secure access for this private network that you might have for maritime services. The first one is called Data Network Name, DNN. In 4G, the same thing was called APN, or Access Point Name. Might be familiar if you have been going through the settings in your phone, that you can find this APN there, for example. So when a mobile phone connects to a mobile network, first there is the 5G access control. So of course we need to have a valid subscription to access the core network. Then after that, the UE, it does the primary authentication to prove that it is kind of authorized. Then it will request to be connected to an external network. Typically your phone will say that, I want to go to internet, and then it will be connected, for example, in this picture via UPF1 to internet. And this happens automatically. However, you can also have the phone request, hey, I want to be connected to this private network that has this DNN private, as we have here in this picture. And with just using this DNN solution, when this request comes to the core network, it will check from its configurations, is this subscriber authorized to access this external network? So it's kind of like a policy in the operator network saying if it's okay to connect there. And if it's okay, then context will be established for this device, and it can it gets an IP address and can connect, and the connection will go to the private network here. And you can see here is a VPN tunnel drawn. This is not something that is mandated, but I think that's kind of a typical scenario when you connect to a private network using DNS. You have some isolation mechanism there that traffic from the core network to the private network is secured and isolated. It could be a leased line as well. Now, the next step here is secondary authentication. So if you're only using DNN, it basically means that only the core network makes this decision. Is it okay to connect this UE to this private network? And if you want kind of one step more on security, you can do what's called secondary authentication. And in this case, when the UE connects to the core network, it says, I want to go to this DNN. The core network will again check, is this subscriber authorized to go to this DNN? Okay, it is. But then there is an additional requirement that it needs to perform secondary authentication before it is granted access. And secondary authentication is basically an authentication between the UE and the authentication server, which typically would be in this private network. So you're authenticating to the private network you want to connect to, that you are actually an authorized subscriber or user of that network. And this secondary authentication is performed using EAP frameworks. You can use various credentials and authentication methods, so you're not kind of bound to the 3GPP credentials here. And basically the operator might not have any kind of insight to those credentials and cannot verify those credentials. It's the AAA server, which here in the picture is in the private network, that kind of is the authorization point. It could of course be in the operator network as well, but this is kind of the typical scenario. And this means that then there are multiple kind of steps of access control performed compared to this plain DNN approach. Then we have network slicing, which is one feature that I think has gotten quite a lot of attention with 5G rolling out. And basically, a network slice is like it's like an own instance of the network or part of the network. So when you request a slice for those parts of the network that you get the slice, you will get kind of an own instance of those network functions. You could have it only for one network function, and you get that for that network function you get your own instance. But you could have it actually end-to-end from the radio access through the whole core network and to the user plane function. So you have a slice where you have own instances of all the network functions. And this helps, of course, then with isolating the traffic of the slice users from those subscribers that are not users of the slice. And when you are requesting access to the slice, you can also be required to do slice-specific access control through slice authentication, which is very similar to the secondary authentication that was discussed in the previous slide. So again, EAP-based authentication can be done there. And of course, multiple subscribers can use the same slice. So we could, for example, have a slice for a specific port. It could have its own slice in an operator providing service in the port and adjacent fairway. So then all, for example, commercial vessels would kind of request to be added to the slice, and their traffic would then go through this specific slice instead of kind of mingling with the traffic of everyone else. And this means that you will have, of course, the isolation, and then also kind of get a type of performance guarantee that you can kind of, you know that your users will use this slice, then you know what type of resources are needed in the various network functions to kind of serve all these potential subscribers. As I said on the previous slide, you can do slicing also on the radio access, and it can be done in different ways. One way is this closed access group. And closed access group is basically that you have multiple subscribers that can be grouped, and they kind of belong to this closed access group. And then they get this closed access group ID, which is configured both to the device and then also in the network. And when a UE tries to connect to the access network can provide a so-called closed access group cell. So there is a radio cell that only accepts users that belong to this specific closed access group. This cell can then have a dedicated radio resource, a dedicated spectrum for this cell. And that means that, for example, this New Year's Eve example, even if it's New Year's Eve, that cell is only serving, or those radio resources are reserved, for example, only for the vessels. So the other people wanting to call and say Happy New Year, they can never access those radio resources. They are always reserved. And the radio resources could be from the pool of spectrum that the operator has, or it could also be potentially that nationally you can put aside certain spectrum for this kind of what I call it, private use, enterprise use. There is, for example, in some countries, spectrum reserved for industry, so that there is spectrum that industry can use locally in their factory, and then the same spectrum can use somewhere else in another factory, and it's not kind of part of the public network spectrum. Yes, and then the final step is private networks. In 5G, they are called non-public networks, or NPN. There are two variants. One is such that part of the private network is provided by a public operator, and part might be provided by a private operator or operated in a private space, like this private external network. And this is called a PNI NPN, private network, public network integrated NPN. And then there is also standalone NPN. And in standalone, it means that the whole 5G network is kind of operated privately. It could, of course, technically be operated by the public network operator, but everything is reserved and hosted privately for the subscribers of this private network. So this could again be that the port has its own private 5G network, and it's all meant for the vessels, for the port equipment, cranes and trucks and whatever there is, and then for the infrastructure in the fairway, sensors and so on. So then you can kind of perform even more isolation compared to the previous solutions that were presented. And this SNPN, for example, can be very useful if you want to have that all data stays on-prem. So then none of the data ever leaves kind of the domain of the private network owner. So if you do slicing, for example, the traffic is isolated from the traffic of other users, but still the traffic is in the public operator's network. But here it would be then in this private network all the time. And one additional benefit that SNPN brings, so the standalone private network, is alternative credentials, which means that instead of using the DIMECC and the shared secret that are the typical 3GPP subscription credentials, you can use basically almost any credentials you want. If you have a certificate infrastructure in place, you can use those certificates to do access authentication, which might be a quite nice feature if you have kind of an existing network which you want to kind of connect to this. So in conclusion, security and availability are key aspects and requirements in maritime connectivity. And 5G provides a bunch of different isolation and robustness mechanisms that can be kind of combined however you want. What I have presented, you can have all of them or some of them and combine how you feel. And kind of combining these access solutions with properly configured secure private network, you can kind of get a quite nice and secure solution overall that should also, in typical scenarios, be robust. Thank you. Any questions?
Any questions or comments? Please.
Is 5G supporting moving base stations? Can ship have a base station communicate with other ship having a base station?
So the ship would act as a base station towards other ships and ships. Well, you could have this private network on the ship, so it would be a moving 5G network.
Authenticate with the land-based network when it comes from
Okay. Yeah, so I would say that if you're an open sea, then one ship could be the 5G network and another ship could be a UE, a mobile phone basically, connecting to that ship's network. When you come and want to connect to the public operator network, then you probably would want to have a modem connecting, and then the base station, I mean, it could be...
I understood some time back that 5G standard doesn't allow to moving base stations, so the kind of bits are mingling around and moving this.
Radio is not my area, so I don't know that I have to say, but like in theory you could have a moving 5G network on the ship moves with the network, but I don't think when it, but if you want to kind of merge it with a public 5G network, that is maybe too complex scenario for me to answer at the moment at least.
Yeah, I mean, we need to remember that the faster you go, the more challenging it will be to really kind of handle the radio. But even with GSM, there is base stations that have been put on ships.
Okay.
So I would say typically probably the base station on a ship is not a problem because they are not moving that fast. But then, of course, there could be some restrictions in standardization anyway on what you can and what you cannot do with a certain radio technology.
Okay, thank you.
Thanks.
Then we move to the last presentation. Awake, and I think you can take all the time you need.
All right.
Yeah.
Tomorrow.
We have nothing better to do. Honor being the last presenter. I hope you bear with me for a while. I'd like to talk to you about our AI system developed in C4 Value. I'm Vice President of AI and Analysis at Awake.ai. Before Awake, I was working at Rolls-Royce Marine developing AI for autonomous vessels. very happy to see many of my former colleagues here today also. Lots of familiar faces. But let's get to the topic. So at Awake, we develop a cloud-based platform for smart ports, analytics, and optimization. And of course, the kind of AI area in maritime logistics is quite wide, but in C4 Valley, we focused mostly on the smart fairways and kind of providing this safety monitoring information for the fairway, but also somewhat on this estimated time of arrival, just-in-time estimations, and also technologies which do support development of autonomous ship algorithms and navigation systems. So in C4 Value, this AI system that I'm talking about has these kind of two very high-level main functionalities. I'll get to the details a little bit later, but I hope to give you like an idea of what the system does first. First is automated predictive monitoring of commercial vessel traffic along fairways. So this means that we monitor global vessel traffic, and we can provide predictions on when the vessel will be on, say, any Finnish fairway. And what this gives us is for remote pilotage. So of course, we can predict the need of pilotage in the future. We can predict congestion along the fairway, and even this kind of, let's say, passings and hazardous times possibly in kind of restricted parts of the fairway. And the other thing is we can do this kind of automated scheduling, RTA, so we can match the schedules of departing and arriving ships, for example, automatically, or provide this kind of proposals on how you could schedule the ships to operate efficiently. So this is one thing, predictions. The other thing is this estimation of dynamic vessel-specific safety margins during pilotage. So this means that we try to find out what is the limit that the pilot or captain has to do something so that the vessel is still within safe bounds on the fairway. And I'll get to this later. The motivation for this is kind of additional decision support for the pilots. This is also a kind of additional backup system independent from the sensor connectivity to the vessel, possibly. This enables kind of automated monitoring of the safe usage of the fairway. So how close to the dangerous limits ships usually are along a fairway. And the components that we develop for this are applicable in developing navigation systems for, let's say, fully autonomous remote pilotage. So we can have a AI which does something that the remote pilot does, or this is applicable for developing autonomous vessel systems where they need to also do these navigation decisions by themselves. So on a very high level, examples of these functionalities. First one was these predictions of schedules. So what we do there is monitor, as I said, all vessel traffic in the world. We categorize the destinations of vessels. And if a vessel is going to a destination of interest, like Vuosaari in this case, we can predict the route of the vessel and kind of points of interest along the trajectory. So here we have, from a couple of days ago, container ship Nord was in the Kiel Canal, headed to Vuosaari. We can predict the route. Along this route, we predict that it will go through this Vuosaari PBA here. So we can give predictions on which PBA it will use, which fairway it will use, and this becomes later for this kind of dynamic fairway simulation. And we can predict these estimated times of arrival to these areas of importance. So of course, the first one would be the PBA, the second would be the port, terminal, or even berth area. And when we do this for all ships coming to Vuosaari, we can have this kind of timeline of congestion and usage of these fairways. Then the dynamic fairway simulation, these safety margins, the idea there is that we continuously monitor the vessel, its speed, heading, the wind speed in this area, the water current, and based on those we calculate these kind of safety margins which the vessel should not get within this red zone to make sure that it is still navigating safely. And of course, this is continuously updated as we get more information along the passage of the fairway. Let's see if I can show you an example. So this is from development. We were using this Viking Express as a kind of test ship, and why it's going to the red area soon is because we were actually deploying in this test the ship model for Viki or Haga to Viking Express, which means that they have very different kind of dynamics, and it was actually going for Viki into a hazardous position here. But you can see as it goes, especially here in this very narrow bit, it's a tricky spot for the pilotage. And this is based on the AIS data here, so we get these updates periodically. Of course, this is a time lapse going very fast. This is the basic concept of the dynamic fairway and this kind of safety corridor. And this was what was shown in the C4 value demonstration. Can I get somehow back to the presentation? Let's see. Sorry. Yes. Of course, this is kind of the simplest thing that we can show for the demo. Of course, the underlying algorithms could also provide these kind of estimates on when you need to start turning, what is the rudder, the thrust. So, you know, the navigation system is doing that or can do that autonomously, but this is just for the first kind of safety feature. Now I want to talk a little bit about how we implemented this. The prediction part I will mainly skip, but to give you an idea of how that works, is we have this kind of pipeline of different kinds of machine learning models, which consume a lot of different data, historical data on vessel traffic. We learn this kind of behavior, how vessels navigate. Then the main components are this destination prediction, which even though with AIS vessels report where they are going, it's not very good. You need to have a lot of intelligence to kind of make sense of that globally. And then the other bigger part is this time of arrival prediction, where we predict the routes, the travel times, pilotage specific delays, and even anchorages in some cases. And kind of technically, we use a lot of different machine learning methods there, various kinds of neural network models, these kind of boosted trees, and for example, graph algorithms. But as the main focus in C4 Valley was this dynamic fairway AI, I'd like to talk about that in a little bit more detail. So the first step in that work was modeling physically the vessels, and of course we started with Viki/Haga. And we have their physical model, which is based on taking into account the various forces acting on the vessel and kind of parameterizing those based on the actual vessel characteristics. So this includes this kind of factors like the thrusts from the thrusters, water friction, wind, air resistance, rudder resistance, residual resistances, torques, and so on. And what we then do is we fit all of these model parameters so that the model ship behaves as the wheelhouse posture of the ship says that it should behave. So this kind of numerical fitting of the model. And the idea is that then this model also contains these kind of wind and current factors which we can then simulate in all conditions. So we have developed these kind of simulation environments where we can model how the ship navigates in different conditions in various wind and current. And we even have made this kind of model predictive control algorithms, which is what the navigation system in an autonomous vessel would use to actually follow a given trajectory. But in C4 value, we mostly use these simulations to estimate these safety margins. So kind of computing over a wide range of, say, wind speeds, wind directions, currents, how the vessel behaves, and what is the needed safety margin for the vessel to be able to turn along the fairway edge. So very simple concept in a way. And what you get out of this is basically like a lookup table, but requires quite a lot of computations to kind of calculate for each vessel type. But this is kind of what's under the hood and what produces this dynamically changing safety margin. So this was the first part of the project, doing these models. Then we did a lot of work to actually implement this as a cloud service. So this is applied in our platform. And we have actual integrations in the demo for vessel position data from Brighthouse and also from Digitraffic. We are using the Fairway specifications from MATLAB, so we can automatically compose the Fairway model that the vessel needs to use. And this service supports these weather variables, wind information, current information, but that was not available in the demonstration from actual sensors. So this is something that could be used in the future also. This is what the architecture looks like. So it is a fairly complex system, but of course many of these parts are something that are in our platform anyway. So the main development was this kind of custom service, which does this modeling that I discussed. It's integrated to Lighthouse data source. Some work for showing this in the web application, and then the prediction features were kind of development of our destination trajectory and ETA models. Well, in the end, this was demonstrated in the final demo in Kokkola. I guess it's nice to end with that. Let's see if I can still access this YouTube. This is quite, let's say, uneventful from our perspective because this fairway is very straight and it was very nicely navigated along the center of the fairway. So there's a little bit of this safety margins happening here in the beginning, but then the vessel mainly just progresses along this long fairway. All right, that's what I wanted to say. Any questions?
Thank you, Jussi. Excellent, good pictures to end the presentation. Any questions? Please.
Really nice presentation. Like for the route prediction algorithm that you're using,
Yeah.
what kind of accuracy are you getting right now when you compare with the actual route?
So yeah, it is based on this kind of global historical data. So even the kind of theoretical accuracy is limited because we cannot model the whole world in like 100 meters accuracy. So we are using this. Well, it's not a grid, but representation for geographical location, which is kind of dynamic. So at the ocean side, we have kind of larger things, and then it goes more accurate as we go to the closer to the land. So it is kind of variable accuracy.
Yeah. So what would you say that what was the most time-consuming part of the implementation? What? Can you name one?
It's hard to say. I think it was quite even. So we spent maybe half of the time on this modeling, and you could go as deep into that as you want. I mean, we were discussing with Novia that we could kind of use the simulators to fine-tune this behavior to get more. I mean, now it's the wheelhouse poster, but you could get better data from simulating actually how the vessel moves. So spend some time on that. But then, of course, the cloud service development, that was more like optimizing and getting all the data feeds to work, efficiently and so on. So a little bit different focus, but maybe it's like 50.
Other question?
Yeah, thank you for the presentation. I had a question about the modeling, the ship. You said you develop physical model. Do you need the exact design data of each ship, or you have a generic model to apply to everyone?
It's a generic model which kind of takes into account these like generic physical properties of things that are like ships. But then we can match these parameters, like let's say how much side wind affects the vessel. That could be one parameter. So the numerical values of those parameters are then matched by simulating. We give some values for the parameters, then we look, does this correspond with what the wheelhouse poster says? So that's like, for example, it does a full turn to the starboard, what is the distance? So that's one kind of metric. And we do a lot of those iterations and then converge these parameters to the actual ship.
So that verification reduces the error compared to the generic model that you use.
Yeah, of course. I mean, without this kind of work, it's like, it's not any ship, it's just very too generic to use anywhere. So this is the kind of optimization you need to do for different ship classes or even individual ships if you want to use this in a larger scale.
Thank you.
Thank you. Any other questions? Okay, if not, I thank you for participation, and we have heard today excellent results of our program. We also heard that there's something still to do, so we don't need to rest in the future. And thank you all presenters, and also you active participation and discussion. And I hope you are safe home journey, but before that you can still stay here a while, have a glass of wine and discuss important matters. So thank you all and see you soon.